120-year-old machine just beat a $2 million computer-controlled press in every single test. Stronger steel, longer life, fewer failures. The Victorian engineers who built it understood something about shaping metal that we've completely forgotten. What if everything we thought made modern manufacturing better is actually making it worse? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. 1905. Sheffield, England. The ground shook as James Nasmyth's steam hammer descended with 50 tons of controlled fury onto glowing steel. The machine stood 3 stories tall, its cast iron frame anchored to bedrock 20 feet below the factory floor. Steam hissed through brass valves as skilled hammermen orchestrated the dance between raw power and delicate precision, forging naval propeller shafts that would power Britain's dreadnoughts across Atlantic waters. No hydraulic leaks, no servo motor failures, no computer crashes that would halt production. Just superheated steam, machine surfaces held to tolerances measured in thousandths, and mechanical control systems that responded to human touch with absolute reliability. The Victorian engineers who designed these machines understood something fundamental. Steel remembers how it was shaped, and the method of shaping determines everything that follows. Fast forward to 2025, and manufacturing engineers face a paradox that defies modern wisdom. Computer-controlled servo presses promise precision, measured in microns, adaptive force control that adjusts thousands of times per second, and programmable sequences that eliminate human error. Manufacturers invested millions upgrading from mechanical systems to electronic sophistication, chasing efficiency gains and tighter tolerances. Yet, in specialty forging shops across Europe and America, century-old steam hammers remain in service, pulled from retirement when modern presses fail to deliver the material properties that critical applications demand. Aircraft landing gear, pressure vessels for nuclear reactors, custom tool steel that must withstand extreme conditions. These components still flow back to machines that Queen Victoria's engineers would recognize. The contradiction runs deeper than simple nostalgia for mechanical simplicity. Metallurgists discovered that parts forged under steam hammers exhibit grain structures that modern presses struggle to replicate. Fatigue testing revealed failure patterns that favored the old methods. Quality control inspectors noted consistency in mechanical properties that electronic control systems, for all their precision, couldn't match. At Kirkstall Forge in Leeds, the last operational Nasmyth steam hammer in Britain faced demolition in 2018. The 120-year-old machine occupied valuable floor space that modern manufacturing principles said should house 4 servo presses. Efficiency consultants calculated payback periods and recommended scrapping the antique equipment. But when aerospace contractors specified forging methods for critical turbine components, they wrote contracts that required steam hammer work, and suddenly the old machine became irreplaceable. The engineering mystery wasn't written in computer algorithms or programmed into motion controllers, but hammered into British iron using principles that treated metal as a living material responding to forces that modern automation had optimized away. The question that haunted every metallurgist who studied the phenomenon was simple. What did the Victorians understand about shaping steel that we've forgotten? Dr. Sarah Chen pressed her hand against the Nasmyth hammer's massive frame, feeling the residual warmth from the morning's forging session. The cast iron still radiated heat absorbed during 3 hours of continuous operation, its thermal mass acting as a reservoir that stabilized temperatures throughout the forging cycle. Steam condensation dripped from overhead pipes, creating rhythmic patterns on the concrete floor that had been worn smooth by a century of foot traffic. "Watch the surface during impact," said Thomas Whitworth, the master hammerman whose grandfather had operated this same machine in 1952. He positioned a steel billet in the dies, its orange glow illuminating his face as he adjusted the placement with practiced efficiency. "You'll see something the sensors on modern presses never capture." Sarah activated her high-speed camera, configured to record at 10,000 frames per second. The hammer fell with a rush of steam and compressed air, striking the glowing steel with force that registered on seismographs 3 blocks away. But, in the slow-motion playback, she observed phenomena that textbooks rarely discussed. The impact wasn't instantaneous. The hammer's mass, over 8 tons of falling iron, compressed the steel progressively as momentum transferred through mechanical contact. The steel flowed outward from the impact point in waves visible on thermal imaging, grain boundaries rearranging under pressure that peaked gradually rather than spiking in milliseconds. Most critically, the hammer bounced, lifting slightly after impact, before the steam system arrested its rebound and brought it down for another controlled blow. Modern servo presses eliminated that bounce through electronic control systems that locked the ram in position with hydraulic or mechanical force. Engineers had treated the bounce as an inefficiency to be eliminated, wasted energy that reduced productivity. But Sarah's metallurgical analysis revealed something unexpected. The bounce mattered. She sectioned samples from both steam hammer forgings and servo press work, etching the steel to reveal grain structure under optical microscopy. The steam hammer parts showed elongated grains aligned in directions that followed the metal's flow during forging, with gradual transitions between zones of different crystal orientation. The servo press samples exhibited sharper boundaries where grain structures changed abruptly, creating stress concentrations that fatigue testing would later expose as failure initiation sites. The bounce lets the steel breathe, Thomas explained, his terminology unscientific but experientially accurate. Lock it solid and you're crushing instead of forging. The metal fights you, traps stresses that never fully relieve. Sarah pulled up force time curves from both processes on her laptop. The steam hammer's impact showed a rounded peak that spread force application over 40 milliseconds. The servo press delivered a square wave, maximum force achieved in under 5 milliseconds, and held constant throughout the forming stroke. Mathematically equivalent energy input, but the steel responded to the time signature of force application with dramatically different internal structures. The principle hiding in plain sight had been documented in 1895 by German metallurgist Adolf Martens, though his observations about impact velocity and grain refinement had been overshadowed by his better-known work on steel microstructures. Sarah discovered his papers in the archives of the Iron and Steel Institute, yellowed pages describing experiments that compared drop hammer forging to hydraulic press work. Martens had measured what he called material response time, the duration required for steel's crystal structure to accommodate applied stress without fracturing. When force arrived faster than crystals could reorganize, dislocations piled up at grain boundaries, creating internal stress patterns that persisted after forging. When force built progressively, allowing time for atomic scale rearrangement, the steel absorbed deformation energy through controlled crystal restructuring. The steam hammer's falling mass created what modern physics would recognize as a momentum-dominated impact. Force peaked as kinetic energy converted to deformation work, then declined as the hammer's velocity reached zero. The entire event spread across tens of milliseconds, giving steel crystals time to respond through thermally activated mechanisms that required molecular motion. Servo presses operated in a fundamentally different regime. Electronic controls commanded position with microsecond precision, driving hydraulic rams or servo motors that delivered specified force regardless of material resistance. The steel encountered what engineers called a stiff system, one that didn't yield regardless of the load's response. Force rose in milliseconds and held constant, creating shock-like conditions that steel experienced as sudden constraint rather than progressive deformation. Thomas demonstrated the difference using a simple analogy. He placed a lump of modeling clay on the anvil and struck it with a wooden mallet. The clay flattened gradually, flowing outward as the mallet's momentum dissipated. Then he positioned another clay sample under a hydraulic arbor press and cranked down the handle. The clay squished flat, but examination showed radial cracks extending from the center where material had been unable to flow quickly enough to accommodate the unyielding advance of the press ram. "Steel's not that different at forging temperature," he explained. "It flows like thick honey, but honey has viscosity. It resists fast deformation more than slow. Push too hard, too fast, and you damage the internal structure even though the outside looks fine." Sarah's finite element analysis confirmed the intuition. Simulations showed stress waves propagating through the workpiece during servo press forming, reflecting from free surfaces and creating interference patterns that concentrated strain in unpredictable locations. The steam hammer's progressive, impact-generated stress fields that evolved smoothly following the metal's natural flow patterns without inducing shock phenomena. The Victorians hadn't understood crystal dislocations or thermal activation mechanisms, but they had observed that metal forged under falling hammers performed better than metal squeezed in screw presses, and they had built their industry around that empirical knowledge. The Schuler servo press occupied the center of the production floor at Forge Tech Industries, its 3,000-ton capacity delivered through 4 servo-electric motors, synchronized to within 0.1 millimeters of parallel ram travel. The machine represented $2.4 million in capital investment, purchased in 2019 to replace aging mechanical presses and increase production efficiency. Programmable force profiles, closed-loop position control, and integrated quality monitoring promised to revolutionize the company's forging operations. By 2023, the Schuler sat idle 3 days per month for maintenance. Servo amplifiers overheated under sustained load cycles, requiring replacement at $8,000 per unit. Position encoders drifted out of calibration, demanding recertification procedures that consumed 2 shifts of downtime. Software updates conflicted with legacy motion control algorithms, forcing emergency calls to German technicians who debugged systems remotely at $400 per hour. But the technical failures paled beside the metallurgical problems. Aerospace customers began rejecting forgings that met all dimensional specifications, yet failed ultrasonic inspection for internal defects. Landing gear components exhibited fatigue cracks during accelerated life testing. Tool steel forgings showed unexpected brittleness despite proper heat treatment protocols. Materials engineers traced the failures to microstructural features that inspection had missed. The servo press's precise force control had created regions of adiabatic shear, narrow bands where rapid deformation generated localized heating that altered crystal structure without visible surface indications. The constant force application had driven metal flow past the point where thermal activation could accommodate strain, nucleating microcracks that propagated during service loading. Quality control implemented additional ultrasonic inspection procedures, increasing inspection costs by 40% and scrap rates by 15%. Process engineers attempted to reprogram force profiles, reducing peak loads and extending dwell times to allow thermal relaxation. Production rates fell, and the efficiency gains that had justified the servo press investment evaporated under the burden of defect management. Meanwhile, at Kirkstall Forge, the steam hammer continued shaping steel with reject rates below 2%. Thomas's practiced hand controlled impact velocity through steam valve adjustments that no engineer could fully quantify. He read the steel's color, watched how it spread under the hammer, listened to the sound of impact, and adjusted the next blow based on sensory information that decades of experience had taught him to interpret. "The machine tells you what the steel needs," Thomas said, demonstrating how hammer bounce varied with workpiece temperature and deformation state. Too hot, and it bounces high, the steel's too soft. Too cold, and there's hardly any bounce, you're working it too hard. You learn to feel the right range, and the hammer does the rest. Forge Tech's management faced an uncomfortable decision. They could continue struggling with the servo press's technical and metallurgical problems, or they could admit that a 120-year-old machine understood something about forging that modern engineering had optimized away. James Nasmyth had sketched the first steam hammer design on a napkin in 1839, solving an engineering problem that had stumped the British shipbuilding industry: how to forge the massive iron paddle shaft for Isambard Kingdom Brunel's steamship Great Britain. Traditional tilt, hammers lacked the controlled power needed for such large work, while screw presses couldn't deliver sufficient force. Nasmyth's insight combined the falling weight principle of drop hammers with steam power's ability to control descent velocity and arrest the blow at any point. But his genius extended beyond the functional concept. Nasmith designed the steam hammer to be fundamentally rebuildable, with every wearing component accessible for replacement and every critical dimension restorable through machining. The massive cast-iron frame wasn't a single monolithic casting, but rather a carefully assembled structure of individual components, each castable by Victorian foundries and machinable with available tools. Sarah examined the assembly drawings preserved in Sheffield's industrial archives, marveling at the attention to maintainability. The hammer's anvil sat on a foundation of compressed oak timbers that absorbed impact energy while remaining replaceable when damaged. The piston, rod that lifted the hammer, traveled through brass guide bushings that wore gradually over decades and could be replaced without disturbing the frame alignment. Even the steam valves used standardized components that mechanical shops could fabricate from bar stock and basic castings. "We've rebuilt this machine completely twice," Thomas explained, showing Sarah the maintenance logs that documented every significant repair since 1905. New piston in 1947, complete recast of the hammerhead in 1973, steam cylinder rebore in 1998. The frame has never needed replacement. That original iron is still perfect. The contrast with modern servo presses couldn't have been starker. The Schuler used proprietary servo motors with custom windings available only from the manufacturer. Its position encoders relied on semiconductor sensors with 10-year typical lifespans. The hydraulic pumps employed specialized seal materials rated for 15,000 hours before replacement. The control system ran on a Linux variant customized for motion control applications, with software updates distributed through encrypted channels that required active maintenance contracts. Nasmith had designed for a world where repair was economically sensible and replacement was prohibitively expensive. Modern manufacturers designed for a world where labor costs dominated capital depreciation schedules and planned obsolescence created recurring revenue streams. The steam hammer existed to be fixed. The servo press existed to be replaced. But the economic calculus was shifting. As servo presses failed before their 10-year depreciation schedules completed, and as aerospace contracts specified forging methods that only steam hammers could reliably deliver, shops began reconsidering which approach actually represented sound long-term investment. The machine that cost nothing to upgrade was beginning to look cheaper than the machine that required constant electronic updates. Sarah compiled the financial analysis that would determine the steam hammer's fate. Capital acquisition cost for the Nasmith hammer in 1905, $850, equivalent to roughly $180,000 in modern currency accounting for inflation. Annual maintenance costs averaged $2,500 across 220 years of operation. Steam valve replacement, bearing renewal, occasional frame repairs. Total lifetime expenditure, including energy costs, approximately $1.2 million. The Schuler servo press purchased in 2019 cost $2.4 million installed. Service contracts ran $45,000 annually. Unscheduled maintenance averaged $30,000 per year. Projected replacement timeline, 12 to 15 years before obsolescence forced complete replacement. Expected lifetime cost over a comparable 120-year period, assuming 6 replacement cycles, $18.7 million, not accounting for increasing complexity and cost in future generations. But the raw numbers masked deeper economic realities. The steam hammer's output could be replicated by operators with 18 months of training. Thomas had learned the craft from his grandfather, who had learned from master hammermen trained in the Victorian apprenticeship system. The knowledge transferred through direct observation and guided practice, requiring no proprietary manuals or vendor certification programs. Operating the Schuler required engineering degrees. Programming force profiles demanded understanding of finite element analysis and material flow modeling. Troubleshooting servo faults required electrical engineering knowledge and access to manufacturer diagnostic software. When problems exceeded in-house capabilities, $10,000 service calls became routine expenses. The productivity comparison seemed to favor modern equipment until Sarah examined actual throughput data. The servo press ran faster cycle times, 12 seconds versus 35 seconds for the steam hammer, but downtime eroded that advantage. Across a full year accounting for maintenance stops, calibration requirements, and failure-induced shutdowns, the steam hammer achieved 87% equipment availability, while the servo press managed 73%. For jobs requiring the metallurgical properties that only progressive impact could deliver, the steam hammer was actually more productive. Energy costs told an unexpected story. The steam hammer consumed 4.2 million BTU per operating day, burning natural gas to generate steam with Victorian-era efficiency. The servo press drew 180 kilowatts during operation, translating to roughly 5.9 million BTU equivalent in primary energy accounting for power plant conversion losses. The inefficient steam system actually used less total energy than the efficient electric servo motors. Thomas provided the final piece of economic context. When the Schuler's down, we lose $5,000 per day in missed production. When this old girl needs maintenance, I can usually patch her up in a few hours with parts from the storeroom. Worst case, we machine a replacement component overnight and she's running by morning. That servo press, we've waited 2 weeks for controllers to ship from Germany. The Victorian hammer hadn't just survived 120 years through superior metallurgy. It had remained economically viable through inherent maintainability and operational simplicity that modern complexity couldn't match. Sarah positioned test specimens in the tensile testing machine, her final experiment comparing forgings from both processes under identical conditions. The steam hammer samples came from automotive gear blanks that Thomas had forged the previous week. The servo press specimens represented the same steel grade shaped to identical dimensions using optimized force profiles that process engineers had spent months refining. The crosshead descended at 0.2 inches per minute, stretching each sample until fracture. Data acquisition systems recorded force and displacement at millisecond intervals, plotting stress-strain curves that revealed how each forging responded to mechanical loading. The differences emerged immediately. Steam hammer forging showed yield strengths 8% higher and ultimate tensile strengths 12% higher than servo press work. More significantly, elongation to failure measured 24% greater in the steam hammer samples. The metal could stretch further before breaking. Thomas watched the fracture surfaces through a stereo microscope, pointing out features that decades of experience had taught him to recognize. See that fibrous texture? That's good metal, properly worked. The grain structure follows the flow lines from forging. He compared it to servo press fractures that showed flatter, more crystalline surfaces. This one looks stronger under the microscope, but it's brittle. The grains are refined, but they're not oriented right. The fatigue testing delivered the decisive verdict. Samples cycled between tension and compression at stress levels, representing service conditions for automotive transmissions. Steam hammer forging survived an average of 2.3 million cycles before crack initiation. Servo press samples failed at 1.7 million cycles, a 35% reduction in fatigue life that would translate directly to premature component failures in field service. Sarah presented her findings to Forge Tech's management team, the data overwhelming in its clarity. The 120-year-old machine wasn't just matching modern equipment, it was producing superior results in the metrics that mattered most for critical applications. The progressive impact that Victorian engineers had developed through empirical observation created material properties that electronic precision couldn't replicate. The decision emerged from engineering reality rather than nostalgia. Forge Tech would keep the Schuler for high-volume work where its speed advantage justified the maintenance burden. But they would also retain the steam hammer for aerospace and automotive forgings where metallurgical performance demanded progressive impact forming. More remarkably, they began designing new steam hammer installations, working with heritage engineering firms to build modern versions using the same fundamental principles Nasmyth had pioneered 185 years earlier. As Thomas fired up the boiler for the afternoon shift, Sarah contemplated the larger question her research had uncovered. If a 120-year-old machine could outperform $2 million in modern technology, what other Victorian engineering principles had we discarded in our rush toward electronic sophistication, and what would it cost to rediscover the wisdom that simpler times had understood?